guys, we're gonna try to do the chapter review for number 13 and on. So here it goes, guys. Chapter 13, number 13. Now this question we studied it in class, but we wanted to finish it. The question goes, there is a curve y equals x to the fourth power, where point about 1 comma 1, what is the curvature of that particular point on that curve? Now, so we can find, we know the curvature here is equal to magnitude of the derivative of tangent vector over magnitude of the derivative of the r vector. Now, but another way which we can do this one from textbook, you will realize that that is equal to r prime cross product with r double prime over r prime to the third power. Now, but the thing is, when we want to do the cross product, it is based upon a 3D-dimensional vectors. So here we only have 2 dimensions. So what we're going to be assuming is this: r of t must be t for x, then t to the fourth power for y, and simply z vector would have been 0, so that we are playing on the xy plane. Now, then here we realize r prime now becomes 1 from 4 t to the third power and 0. Now, how about r double prime? Then we get 0 comma 12 t squared comma 0. Now, since this point can be found when t is equal to 1, so r prime now can become 1 comma 4 comma 0, where r double prime can now become 0, 12, and 0. In order for us to calculate the curvature, then now simply becomes r prime cross product with r double prime now simply becomes determinant of this matrix 1, 4, 0, 0, 12, and 0. Here now we get I minus j and then k. Let's try to evaluate it. Coefficient of I, you will realize it to be equal to 0. Coefficient of j, you will realize it to be equal to 0. And coefficient of k, in fact that would be equal to 12. And this is rather easy to find out the magnitude is equal to 12. Now, how about magnitude of r prime? Is square root of each component right here, 1 squared plus 4 squared plus 0 squared, which now to be square root of 17. And I believe that we can easily find the answer here now. It becomes the numerator for the curvature becomes 12. And denominator becomes square root of 17 to the third power. In other words, it becomes 12 over 17 to the 3 over 2 power. There it goes. That becomes our final answer. All right, now let us move on to the next question, number 15. Find an equation of the osculating plane. Now, in this case, the fact that it's an osculating plane, that means it's a plane that contains the tangent vector and normal vector. That means we need to find a vector, because in order for us to find the equation of a plane, one thing that we need is point and normal vector to the plane. That's what we need to find. In order for us to find the normal vector to the plane, in fact, this basically can be found by tangent vector cross product with the normal vector of the curve. Now, in fact, if you know, in order for you to get the unit tangent vector and then unit normal vector, it will be some out of calculation. So what we like to do is I'm going to try to do this question a little bit differently in a way that we will assume that normal vector to the plane will be in fact parallel. So the direction of the tangent vector can be found. Direction of the tangent vector will be parallel to r prime, and then direction of the normal vector will be parallel to r double prime. So therefore, we'll be calculating this to get the magnitude of, or the direction of the normal vector. Now, then, let us try to do this one together. Normal vector, in order for us to get that, we want to, normal vector to the plane, in order for us to get that, we're going to figure out r first. What is r here? R of t, for this particular question, was sine of 2t. And t and cosine of 2t. As you can see, this will be the equation of an helix, circular. So therefore, we will realize that as you take each derivative, it will always be perpendicular to each other. Now, then let's try to find out r prime. R prime now here becomes 2 cosine of 2t. And then 1 negative 2 sine of 2t. Or in fact, since we didn't practice finding out the unit tangent vector, in fact, we can try to just get the unit tangent vector. Actually, it's not a big problem here. And then in order for us to get unit tangent vector here, it would have been this. It will be simply 2 cosine of 2t and 1 and negative 2 sine of 2t. But divide whole thing by its magnitude. Now you will realize the magnitude of this one simply becomes 4 cosine squared 2t plus 1 4 sine squared 2t, which will be equal to, the denominator now becomes simply square root of 5. Now, then, if you want to go further, the normal vector, unit normal vector, in fact, to the curve now becomes 1 over square root of 5. And then we'll be taking the derivative of the numerator, which would be now becomes negative 2 sine of 2t comma 0. And then here we end up getting negative 2 cosine of 2t. Now, what we have done is the derivative, this portion is the derivative of the tangent vector. Now we need to divide the whole thing by the magnitude of this tangent vector. But once again, you will simply be able to calculate the magnitude of this tangent vector. Here becomes 1 over radical 5 times the magnitude of this portion, which now becomes simply 2. Now, then here, all these things has to happen when point was 0, pi, 1. Now, the fact that point is 0, pi, 1, that means t has to be equal to pi. So let us try to get the numerical value for unit tangent vector and also normal vector. Here then we have tangent vector now becomes square root of 5, and when you plug in pi, here we get 2, 1, 0. And normal vector, we can simply cancel these two things out, and here we get 0, 0, negative 1. Now, then when we try to do the cross product of those two, in fact, the normal vector to the plane, I'm just going to take this one off the beginning. Well, now simply becomes 2, 1, 0, cross product with 0, 0, negative 1. Now we'll be able to simply calculate, is ijk 2, 1, 0, 0, 0, negative 1, then 1 over radical 5. Here we get I negative j k. And I now becomes negative 1. J becomes negative 2, hence making it into positive 2. K will be equal to 0. Now, since this is a vector, and it will be simpler if you to just represent it with this portion of the vector without multiplying by 1 over radical 5, because they're all parallel by the scalar product of 1 over radical 5. So what we end up doing now is this. The point was 0, pi, and 1. And vector now is negative 1, 2, and 0. So therefore our equation becomes x minus 0 and negative 1. And then plus 2 from right here, we get y minus pi. And the rest of them will become 0 and z minus 1. We realize that it's equal to 0, so we end up, our final answer is negative x plus 2y is equal to 2. Pi will be our final answer.